Hey everyone, we're beginning our next video here on AP Calculus, the Calculus B final review, and we're looking at question 30 here. Find the volume of the solid that lies between the planes perpendicular to the x-axis at x equals 1 and x equals -1. The cross-sections perpendicular to the x-axis whose diagonals run from the semicircle negative root 1 minus x squared to the semicircle root 1 minus x squared. So this is a little weird sounding, but we'll try to kind of talk you through what's going on here. The first thing I like to look at is the base of the triangle. Sorry, the base of the solid. So when we say that the base, the cross sections run from semicircle negative root 1 minus x squared. Well, the negative root 1 minus x squared, that's this bottom curve here. It's a semicircle. And it goes to the positive root 1 minus x squared. And that's going to be this one up here. So if I draw a segment that is perpendicular to the x-axis, that goes from one of these semicircles to the other, I'm really talking about something like this rectangle that goes from the top to the bottom, from the red curve to the blue curve. That's going to be my L. The equation of L, or the distance from the top curve to the bottom curve, that's going to be equal to the y-coordinate at the top, which is that the y-coordinate is root 1 minus x squared, minus the y-coordinate at the bottom. And the y-coordinate at the bottom here is negative 1 minus x squared. When you put all of that together over here, that's just equal to 2 times the square root. And that does it for our L, really. L is 2 root 1 minus x squared. So we don't need those bases anymore. Now we need to know about the cross sections. So the cross sections perpendicular to the x-axis are squares whose diagonals run from semicircle to semicircle. So if the diagonals are going from a semicircle to a semicircle, that means L is going to be the diagonal, because L is a length that's going from semicircle to semicircle. So L is going to be the diagonal of one of these square cross sections. We'll put this diamond shape here to represent the square, and now we need to we'll put our L here next. Where is L on this square? Well, like we were saying with the problem, the diagonal is the thing that's going from semicircle to semicircle. So this diagonal here is the same as this diagonal here. So you can imagine what's going to happen is you're going to have a shape where the above the circle is going to be half of the upper half of this square, and below the circle is going to be the lower half of the square. In any case, what we really need to do next is to figure out the area of this square using L as our measure. Now, if you remember that we're dealing with a square here, then it shouldn't be shocking that these two angles that I have marked here, these are going to be 45-degree angles. And then when I drop in the height here, we're looking at on the right side here, we're looking at a 45, 45, 90 triangle yet again. And this side, the base of this is going to be square root of L, sorry, half of L. And because it's an isosceles triangle, the height here is also going to be half of L. So basically, the height of this triangle, the upper triangle, that's going to be L over 2. So if I need to find the area of this square then, well, then we could say that the area is equal to the area of the upper triangle plus the area of the lower triangle. That's going to be the area of the square. the upper triangle, just to refresh our memory. The upper triangle means this whole part up here, and the lower triangle is going to be all of this down here. Now they are actually the same triangle, so as soon as we find the area of the upper triangle, that's going to be the same as the area of the lower triangle. Well, let's find the area of that upper triangle. Zooming into that upper triangle, we can see that the base of the upper triangle is going to be L. This diagonal was L, pretty much by definition. And then the height of this upper triangle is going to be L over 2. So if I was to put the formula here, the area of the upper triangle is going to be 1/2 of L multiplied by L over 2. And that simplifies into 1/4 L squared. The lower triangle has the exact same area as the upper triangle, so its area is also 1/4 L squared. And when we add that together, we get that the area of the cross-section is 1/2 L squared. Now that's going to help me greatly because I actually also know what L is. So let's go ahead and put that together with L. The area is 1/2 L squared. And from this equation over here, we can see that L is 2 root 1 minus x squared. Substitute that in, and then we're going to square. We could square the 2 and the square root separately. 2 squared is 4. 4 times 1/2 is 2. The square of the square root is just the radicand. So we end up getting that the area is just 2 times the quantity of 1 minus x squared. Or if you prefer, that's 2 minus 2x squared. So this is everything we're going to need to figure out our volume. The volume is the integral from a to b of the area formula. Based on the circle, since the radius is 1, a and b are -1 and 1. And the area formula is 2 minus 2x squared. Well, perfect. The next thing that I want to do is to notice that we can take advantage of symmetry, since the left side here is going to be congruent to the right side over here. We can just integrate from 0 to 1 and double the result, and that'll give us the same volume. So we'll change that lower limit to 0, and then we'll double the whole thing, and that will give me an equivalent integral. All right, now the antiderivatives are not so bad. The 2 is going to stick with us. I should point out that this 2 here is this 2 right here. They are the same thing. The next thing is the antiderivative of this 2, which is 2x, followed by the antiderivative of 2x squared, which is 2/3 x cubed. And we're going to be going from 0 to 1. Okay, so this is equal to the antiderivative evaluated at 1 minus the antiderivative evaluated at 0. Now we'll work on the algebra. 2 times 1 is 2. 1 cubed is 1, and then multiplied by 2/3 is just 2/3. 2 times 0 is 0. 0 cubed is 0. Multiplied by 2/3 is still 0. We'll do some subtraction next. 2 minus 2/3, that's 4/3. 0 minus 0 is 0. Now we'll multiply again. 2 times 4/3 is 8/3, and 2 times 0 is 0. And of course, 8/3 minus 0 is just 8/3. And that just about does it for this problem. Our volume is 8/3. Okay. Backing up a little bit, let's take a look at this next one, number 31. We're supposed to write an integral that can be used to find the volume generated by revolving the shaded region about the x-axis. So we've got a lot of good information up over here. Let's just review it. This line over here is x equals 5. This line down over here, this is y equals 0. And this line over here, this is y equals 3 minus 6 over x. It looks like we're going from x equals 2 to x equals 5. And if I draw my radius around the axis of revolution, I get that the radius goes from this y-coordinate up here to this y-coordinate down at the bottom. Now the y-coordinate at the top, that's on this curve, which is 3 minus 6 over x, minus the y-coordinate here at the bottom, which is always going to be 0. All of this gives me that the radius is just going to be equal to 3 minus 6 over x. Looking further at the problem here, we're revolving the region about the x-axis, okay, around the x-axis, and the x-axis is also a boundary for my shaded region. So that means that we are going to just need to utilize the disk method for this. So the disk method says that the volume is just going to be equal to pi r squared dx from a to b. And we know our radius is equal to 3 minus 6 over x. Now, I'd like to remind you that earlier here we said that the smallest value of x here is going to be 2, and the biggest value of x over on the right side is going to be 5. So that's going to be my lower limit. A is 2, and b is going to be 5. And now that I have my integral set up, I can kind of move away from the figure and just start concentrating on integrating. Now the first thing I see here, I see that I have a square right there. So I'm going to expand this binomial. And now I can set about finding the antiderivative term by term. The antiderivative of 9 is 9x. The antiderivative of 36 over x, that's 36 natural log of x. And then the antiderivative of 36x to the negative 2 power, that's negative 36x to the negative 1 power. And we still have our lower limits 2 and 5. Next task for us is to substitute our upper and lower limits into our antiderivative. So we'll get our antiderivative, start substituting 5 minus our antiderivative, substitute 2. Okay, inside of our antiderivatives now, we'll go ahead and do some multiplication. Inside our antiderivatives, we'll do some subtraction. And then because of these square of these natural logs, I think I'm going to distribute the pi's. We'll do a little reordering. We'll factor this 36 pi. And then use some properties of natural logs, or just any log really. And that pretty much does it, except for maybe a little bit of a cosmetic work. And yeah, that looks pretty good. Let's see our next question here. I think this might be our last one. Now maybe we have a couple more. Let's see. Find the volume of the solid form by revolving the region bound by root x minus 2, y equals 0, which is the x-axis, and x equals 6 about the x-axis. The graph of this region kind of looks like this, where this parabola shape here, that's the square root of x minus 2. This is the x-axis, that's going to be y equals 0, and this is x minus 6. Also, we're being told that we're revolving this around the x-axis, so this is our axis of revolution, and that happens to be one of our boundary curves. So right off the bat, we're saying that since the boundary curve is the axis of revolution, we're going to create a disk instead of a washer. Let's get the value of r. Oh, I also should point out, I always forget to do this, that this literally says revolving. So this is a pi r squared region. This is a circular cross section. Okay, the next step here is going to find a typical value of the radius. And for the radius, I always like to say we're going to be drawing a line from the axis of revolution to the region, through the region, and to the outer edge of the region. And that's going to be our radius. The fact that we're starting at the axis of revolution enforces that this has to be our radius. Just like every other radius, we need to find the y-coordinate up here, and because that's on top, and that y-coordinate is root x minus 2, since that y-coordinate is on that square root function. And then from that, we're going to subtract the y-coordinate at the bottom of the radius, which is the axis of rotation, always the axis of rotation. And in this case, that's going to be the y-coordinate is going to be equal to 0. Now that we have our radius, we're going to take a look at our cross sections. Since we're revolving, here's that word again, revolving. Since we're revolving, our cross sections are circles, so the area formula is pi r squared. We have an equation for r. R is root x minus 2, which is going to simplify very nicely into pi multiplied by the quantity of x minus 2. All right, area formula out of the way. All that's left is our integral. The volume is always the integral of the area. Taking a look at our region, our lower limit for x is 2. Our upper limit for x is 6. And also we have our area formula is pi x minus 2. And we are now ready for an antiderivative. The antiderivative of x is 1/2 x squared. And the antiderivative of 2 is 2x. And our lower limit is still 2, and our upper limit is still 6. Now that we have our antiderivative, we're ready to substitute. So let's take our antiderivative, substitute 6, minus the antiderivative, substitute 2. We'll do all the squares. Then we'll do all the multiplying. We'll do our subtraction. And then we'll add. And that takes care of our problem. Question 33. This is definitely going to be the last one in our video. We've got to write an integral that, when evaluated, will give the length of the curve of 9 minus x to the 2/3 power from x between 1 and 8. Now for these problems, we're going to start off by trying to figure out our derivative. if we start with y equals 9 minus x to the 2/3, then the derivative of y is equal to the derivative of 9 minus x to the 2/3. The derivative of y with respect to x is just dx. The derivative of 9 is 0. The derivative of x to the 2/3, negative x to the 2/3 that is negative 2/3 x to the 2/3 minus 1, which is negative 1/3. Okay, now we're going to square that. The square of the left equals the square of the right. Since I'm squaring, this negative sign is not really necessary. Square of a negative is the same as the square of a positive. We can separate this out a little bit, which means we can square each factor separately. And then the square of 2/3 is 4/3, 4/9. And then the square of x to the negative 1/3, that's 4/9 x to the negative 2/3. Well, x to the negative 2/3 is 1 over x to the positive 2/3. And you could just multiply that all together. That's probably more simplification than we needed. Well, in any case, we'll just go ahead and get to our integral for the length of the curve. Okay, the length is equal to the integral of the square root of 1 plus dy dx squared dx. And of course, I have an equation for the square of dy dx. It's right over here. So we'll just pop that right into this equation. And we'll be done with it. Oh, I'm sorry. We need the x is going from 1 to 8. So we'll change a to 1. We'll change b to 8. And this integral, when you evaluate it, will give you the length of the curve y equals 9 minus x to the 2/3 from x equals 1 to x equals 8. And that is the end of the part 1 videos. Next time we come back here, I'm going to be looking at these calculator questions, and we will see you later for that. Have a good one.